Hey everyone, in today's video we're going to talk about impact events, and we're going to perform the analysis in terms of an impulse. Impulse is an instantaneous change in momentum. So let's set up an example problem. We have a player with a bat. This could be baseball, it could be cricket. There is a ball pitched at them, they swing their bat, there is an impact event between the ball and the bat, and the ball experiences a very sudden change in its momentum. It had momentum in one direction, now it has momentum in the other direction. We know Newton's second law. Sum of forces is going to be a change in momentum. We can actually integrate both sides of this. And if we do, well, let's just leave the left side as it is. Sum of forces on A, dt, and let's do this over some bounds, t1 to t2. The right-hand side, we will have the momentum of A at time 2 minus the momentum of A at time 1. Now, what information do we have? Let's say that we know the momentum of the ball going into the impact. So this would be the mass multiplied by the velocity. We don't know the momentum coming out. And what about the forces acting between these two bodies? Well, we probably don't know this either. So we can see that there's a series of unknowns in predicting this behavior. So where does an impulse come in? Well, impulse, we have these forces acting over this time period. And imagine that this window, T1 to T2, so here is T1, here is T2, and we have some forces acting over this. So let's say this is, here are the forces acting on A. And it's not necessarily constant, but there is some forces acting over this time period. And we don't explicitly know what those forces are. Suppose that this time period, T1 to T2, suppose that this time period is shortened. So we theoretically cut it in half. That means we actually need to increase the magnitude of the forces such that the integral of the forces acting over this time period, right, such that this is maintained because the ball has a change in momentum. And this is actually the change in momentum, the forces acting over a certain amount of time. So what happens if we take this time window and we move it all the way in such that there is no real time period? It is an instantaneous change in momentum. Then what's going to happen is the magnitude of these forces will actually shoot up to infinity. As this window goes to 0, the magnitude of the forces will go to 0, the magnitude will go to infinity as the time goes to 0. And that, when the forces spike, that is what we call an impulse. It has the same units as momentum impulse does, and it's going to elicit an instantaneous change in momentum. Now, is that actually what is happening in the problem? Well, no. We know that the ball and the bat are physically in contact for a period of time. Maybe it's, depending on whatever phenomena we're looking at, maybe it's microseconds, maybe it's milliseconds, but there is a period of time where the ball is in contact with the bat. What we're going to do is we can assume that it's effectively 0, and we're going to call that an impulse. Okay. So what we need to do is we need to come up with a series of equations that define how this ball and this bat interact. Now, we're going to inject into this problem the assumption that this is inelastic. We could perform some kind of, we could approach this as maybe a conservation problem. We could say that whatever energy this ball has going in, it's going to have the same energy coming out, something like that. What we would actually like to do, though, is we would like to include in this analysis some inelasticity, which is energy is going to be lost. Perhaps there is some internal friction inside of this ball, right? We know that objects can compress. We know that objects they'll have internal friction, so some energy is going to be lost in this process. So this is the analysis we're about to do. This is a way of modeling not only the impact event, but also some loss of energy as well. Okay, let's clean this up, and what we're going to do is we're going to focus on this impact event. Let's assume that we have two particles. These particles are going to collide, they're going to hit, there's going to be an impact event, and then they're going to separate. Let's start with some diagrams. We have particle A and we have particle B. So right now at the beginning of the problem, they haven't impacted yet, so they're in an approach phase. They each have a velocity, VA and VB. Next, we know they're going to collide, so let's draw that collision. Here's body A, here's body B, and this point between them where they're touching, this collision point, let's call this point C. So here's our impact event. And then sometime in the future, the bodies have separated again. Here's body A, here's body B, and now they have different velocities, VA and VB. So clearly this impact event has caused a change in the momentum of each of their bodies. And if we say that this impact event, it's a very small time window, that means that there's effectively some impulse between these two, right? It's some force between them acting over a very small time window. So let's characterize the time for these periods. Let's say that here in the approach phase, time is less than time number 1. So time number 1 then is when during the impact. I'm actually going to say though that this impact event, we're going to break it into a series of phases. So let's say that the time period for this impact event is actually T1 to T3. And we're going to take this period and we're going to talk about what's going on. And then the separation phase, time is now greater than T3. So what's actually happening inside of an impact event like this? Well, let's do this. Let's take this one small event and let's break it into a series of free body diagrams. So I'm going to draw. Here's the impact event, and we're separating it. The first phase of the impact, I'm drawing the bodies separated because we're doing a free body diagram. But remember, these bodies are in contact. So body A, body B. And what's happening in this first phase is the bodies have come into contact. They're touching at point C, but at that instant where they first come into contact, they haven't lost any of their momentum. The bodies themselves still have momentum. So the centers of masses are still translating towards each other, but the contact point C cannot move. What that means is the body itself has to deform. It has to compress just a little bit. It's going to squish like a spring. So this period right now, what that means is the bodies are actually pushing against each other, and they're going to compress just a small amount. So there is a force acting between these, and let's call it Fc. The C is for compression. So here's the first phase of our impact event. It's this compression phase. Next, eventually this force Fc. Whoops, I actually drew it in the wrong direction. There we go. Compression force. Okay. If body A is translating to the right, we need a force acting on it to the left to bring it to a stop. Eventually it does bring it to a stop. So here are the two bodies, A and B. And at this point, when the bodies have come to, let's say, a relative stop, they could both still be translating, right? Here's two objects in my hands, and these objects are both translating because I'm on planet Earth and I'm spinning, right, and planet Earth is spinning around the sun, etc. So the bodies could still have some kind of momentum. It's that their relative velocities have gone to zero. So this was the compression phase. This phase is now maximum compression, so I'm just going to say max maximum compress. So here's our maximum compression. Next, the bodies have, the relative velocity between the bodies have gone to 0, but the bodies themselves have deformed just a little bit, and we're saying that they're going to function a bit like springs, which means they're going to now push back. So body A, body B, and there is now a force pushing back on both of these. This force, it's not a compression force anymore because we're not squeezing the bodies. Now it's the bodies attempting to return to their original shapes. This is called restitution. So I'm going to put F sub R on those bodies, a restitution force. Notice that the restitution force acts in the same direction as the compression force. Compression force is going to bring body A to a stop, and then the restitution force is going to push back, and it's going to cause it to accelerate now into the other direction. So what's the time windows? Well, we said this whole event takes place in the window T1 to T3. So I'm going to say there's a T2 right in the middle. This is our maximum compression, so T equals T2 at maximum compression. So the window then for the compression phase, this is time, and it's in between T1 and T2. And then the window for the restitution phase, time is in between T2 and T3. Now, I've written all of these as inequalities. Feel free to put the equals, right, wherever you want to call the equals on these. There we go. Less than or greater than equal to over here, that's fine. All right, what else do we know about these events? Well, as I said, during this maximum compression phase, the relative velocity between the two is going to go to 0, which means VA equals VB at time 2. So we could also add we could specifically call this out. We could say that VA at time 2 equals VB at time 2. All right, here's what we need to do next. So I need to erase all of this, but what we're going to do is we're going to take these free body diagrams for the compression phase and the restitution phase, and we're going to write a series of equations. Let's do sum of forces on bodies A and B at over the period for the compression phase and the restitution phase. We have two bodies, A and B. We have two time periods, compression and restitution. That means we can write 4 equations. So these are coming from the free body diagrams, and I'm going to write these as changes in momentum. So the first equation, we're going to do the time period T1 to T2. So this is the compression phase, and we're going to look at body A. The force acting on body A was Fc, and it's acting in the negative x hat n direction, dt. Okay, so I have written it as the integral, which means the right-hand side of the equation then is the change in momentum. So we have ma va at time 2 minus ma va at time 1. Okay. The specifics for this problem, this is probably VA. This is probably Q1 dot at time 2, and this is Q1 dot at time number 1. So for this specific problem, we could just track the motion in the x hat n direction. In a more general problem, of course, these are vectors. Next, here is this is compression phase for body A. What about compression phase for body B? Integral. It's over the same time period, T1 to T2. It's the same force, Fc. It's now acting in the positive x hat n direction. So dt, and of course the right-hand side, mb, vb, at time 2 minus MB VB at time number 1. And of course, the specifics for this problem, if we do Q1 for body A, we're doing Q2 for body B. So Q2 dot at time number 2 minus Q2 dot at time number 1. We can put the mass MB and MA. Okay. Restitution equations are effectively the same. The only thing that's going to change is the time period. We're now looking T2 to T3. So for body A, we no longer have a compression force, we have a restitution force. It's still acting in the negative x hat in direction, and it's still equal to the change in momentum. MA, VA, the time bounds now are T3 minus time 2. And then for body B, time 2, time 3, the restitution force in the positive x hat in direction. And then change in momentum of body B. So MB, VB, T3, MB, VB, T2. Okay. And of course, you can go through and you can put in the specifics about the Q dots. At this point in the analysis, we have 4 equations. We did compression for A and B, restitution for A and B. In those equations, if you go through and count them up, you'll find 8 variables. There's the compressive force, the restitution force, speeds at time 1, speeds at time 2, and speeds at time 3. Now, with 8 variables and 4 equations, we can't solve for any one of these variables, which is what we want. We want to be able to solve probably for these final times. We want to know the velocities after the impact, which means we need to either constrain away some of these variables or we need additional equations. Well, what other information do we have about the system? Let's say, for this discussion, let's say that we have some information about the initial speeds. So we know VA at time 1 and VB at time 1. Let's say that those are known. Next, what else do we know? Well, I'm actually going to write in VA at T1 and VB at T1. These are known. Okay, so that if we have these, that's like saying you have 6 equations and 8 variables, or we could subtract those 2 away and we could say 4 equations, 6 variables. Okay, so we need 2 more bits of information. Well, we did say that at maximum compression, at time 2, VA equals VB. So let's write that equation down. VA at time 2 equals VB at time 2. All right. So that brings us up to, let's count these as equations, that brings us up to 7 equations with 8 variables. At this point, we need some other information to solve this system explicitly. What we're going to do is let's introduce a new parameter. We call it the coefficient of restitution, and that parameter is going to help us solve this system. What if we made this claim? What if we said that the integral from T1 to T2 of the compressive force, what if this was equal to the integral T2 to T3 of the restitution force? Well, if you integrate the force, then this is momentum. So whatever the change in momentum elicited by the compressive force, that's equal to the change in momentum elicited by the restitution force. Well, this would mean, this would be kind of a conservation of momentum problem. We could say that the momentum at the 2 sides of the impact event were equivalent. What we want to do is we want to say these are not equals. If they're not equals to each other, this means that you have some deformation. And consider, if they're not equals, which one is greater than the other? That means that the compressive force is greater than the restitution force. That means you squeezed your body, right, and the compression brought it to a stop, And then when the bodies pushed back against each other, they didn't push back quite as hard, which means you have now some deformation of your body. If we flip the inequality, if we say that the restitution force was somehow greater than the compression force, that means you have more momentum after the impact, which is not possible. So we're going to make this claim that some deformation has happened, and we need some way of characterizing that deformation. So as I said, there's a coefficient of restitution that is going to define the relationship between these. Now there's several different coefficients of restitutions. There is, for example, Poisson's. There is Newton has one. There is another one by a guy named Strange. I think that's how you spell his name, Strange's coefficient. I'm going to give you the equations for the first two. So here is Poisson's definition of this coefficient. He defined it as the ratio of the restitution force over the compression force. And I'm going to drop the bounds and the DTs. We know that they're attached. So what kind of values would Poisson's coefficient of restitution have? Well, as we said, the compressive force is greater than the restitution force. So Poisson's ratio then is bounded. We use the letter E. So E sub r is bounded between 0 and 1. What would a coefficient of restitution of 1 look like? That means, again, that these two values are equal to each other, and no energy is lost during the collision event. What if you have a coefficient of restitution of 0? That means that there are no restitution forces. That means your object, it struck the surface and it compressed, and then it didn't push back. It had no restitution, which means it just dropped, right? You strike the surface and then you effectively stick to the surface. You don't bounce back. Depending on the nature of the collision, we throw a ball and then it has some kind of bounce and some kind of bounce. Perhaps this first bounce has a coefficient of 0.6, and the second bounce had a coefficient of 0.85, and the next one of 0.8, etc. The value of this coefficient of restitution, it's usually done through experimentation, and we can characterize these things from data. It's a function of the geometry and the material properties, and perhaps the humidity or the slickness on the surface, or what part of your object has come in contact with the surface. But either you collect all of your data and you solve for the coefficient, or you can assume some value of the coefficient, and then that allows you to perform the analysis moving forward. Next, let me give you Newton's coefficient. So Newton, same symbol, E sub r. He defined his also as a ratio. His is not the ratio of the integral of the forces. His is the ratio of the relative velocities between the final and initial values. So let's say VB at time 3 minus VA at time 3. So these are, again, the finals. And then VB at time 1 minus VA at time 1. Okay, and again, there's numerous ways to define a coefficient of restitution. You actually have to apply this in your final problem for homework 10. I'm going to ask that you use Poisson's definition for that problem. Okay, so this gives you all the tools that you need to solve that problem. I'm going to make another video in which we do a worked example of how to apply this. But for now, this is it. So have a great day. I hope you're doing well. I'll see you next time.